Yes, so hopefully I am audible. Okay, so I have put the video of today. Okay, now we will move on towards our lecture number 7 of physics optional paper 2. Up to the lecture number 6, we had seen this thing that the 3D time dependent Schrodinger equation. Okay, what was 3D time dependent Schrodinger equation? It was like this, right? 2m delta square, okay, plus Vr, ठीक है, psi r comma t equal to I h cut del by del t psi r comma t, right? This is suppose your equation number 1, and this is what time dependent Schrodinger equation we had learnt up to here in the previous classes. Okay, this is time dependent form of Schrodinger equation. Okay, now what is time independent form of Schrodinger equation? We will move on to that, but before learning that, I would like to give you some information that what is the difference between this notation and this notation. Okay, so this notation basically implies that it is capital psi. Okay, it is capital psi, and this notation implies that it is small psi. Okay, this is small psi. What is the difference between the two? This is used to represent time dependent Schrodinger wave equation. Okay, the capital psi is used to represent time dependent Schrodinger equation, and the small psi is used to represent time independent Schrodinger equation. Okay, this is used to represent time dependent Schrodinger equation, and this is used to represent time independent Schrodinger equation. Okay, so this is the difference between the two, that if you find two horizontal bars over here, then it is capital psi, and if there are no horizontal bars, then it is what? Small psi. This is the thing which you have to observe. In the books it might be written like this, might be in the bold form, and this may be unbold. Okay, in the books it may represent like that. Okay, in the books they may represent like this is bold. Okay, old psi, so they will say it to be time dependent. Okay, time dependent in the books I am saying. Okay, they will bold it basically. Okay, and the unbold form. Okay, so the unbold form will be unbold, that will be time independent in the books. In the books, so in the books this is the thing, and while we are writing we can't bold, right? Because we are writing with the pen in the exam. As we are writing with the pen in the exam, we don't have time to bold any letter over there. So simply we use capital psi for time dependent Schrodinger wave equation, and we use small psi for time independent Schrodinger wave equation in the exam. But in books, in some books this is the case. Okay, and some books use this also, but in some of the books this is the case, they use bold psi. Okay, so they will suppose show it like this. Okay, they will show it like this in the bold form. Okay, and this is unbold, this is unbold one, so this is time independent, and the bold one, that will be time dependent. Okay, now we will now I want to tell you the difference between uh, complete derivative and partial derivative. Okay, when I say complete derivative, what does it mean is that when you take the d by dx of xyz, suppose xyz t, suppose, okay, then what will happen? Ultimately, you will get dx by dx yzt, okay, plus x dy by dx zt, right? Then you will get basically xy del z by del x t, and then the final term will be x y z dt by dx, right? So these are the things which you have to remember. This is true for full derivative. Okay, full derivative symbol. Now what about partial derivative symbol? In the partial derivative symbol, suppose this is written, okay, then what will happen in partial derivative is that y, z and t will be treated as constants. So y, z and t will come out of the differential, and it will be simply like this, and it will become yzt. Okay, so this is basically your what we can say partial derivative. Okay, partial derivative. It is represented like this. Okay, but the complete derivative, the definition is like this, that in complete derivative, x y z y z t are not independent. Okay, like y z t will also when you take the differentiation over here, this differentiation will not become zero. Okay, it will have some finite value. This differentiation will not become zero. This differentiation will not become zero. It means that yzt will be treated as constant in front of, will not be treated as constant in front of x. Okay, so let me write over here. Suppose del by del x, x y z t is over there. Then I would say that y z and t are not constants with respect to x. Okay, so y z t are not constants with respect to x if I write full derivative symbol. Okay, complete derivative symbol. But if I write the partial derivative symbol, okay, then y z t are constants with respect to x. Okay, so in this case yzt are constants with respect to x, and in this case yzt are not constants with respect to x. So this is a very simple derivative, and this will be a little bit complicated. You will have to use the uv formula. You will have to use uv formula over here. Okay, over here you will have to use uv formula, but over here xyz will be treated as constant. Say the constant will be like this. Suppose del by del x xyz t I have to find. Okay, so yzt are constant with respect to x, right? Yzt are constant with respect to x. So what will happen is that let us say yzt is equal to c, suppose. Okay, so I will just put the value over here, that it will be xc. Okay, then c will come out of the derivative. Okay, del by del x of x, and it will become c, and this c is equal to yzt. So your final result is yzt, right? But in the complete derivative this will not happen. In the complete derivative, you will have to use the uv formula. So if you use the uv formula, clearly yzt will remain. Okay, then x will come, dy by dx will come. Okay, z and t will remain. Okay, then x y del dz by dx will come, t will remain. Okay, and then x, y, z dt by dx will come. Okay, so this is the form of complete derivative. You have to use the UV formula. Okay, so this is the difference between complete derivative and partial derivative. Okay, now suppose if I say that I write this symbol. Okay, and if I say that y, z and t are constants, if I say like that, y, z and t are constant with respect to x, if I say like that, then clearly this term will vanish, this term will vanish, because this will become 0. Okay, okay, this term will also vanish because dz by dx will become 0, and dt by dx will also vanish because I have already told that y, z and t are constant with respect to x. So del dy by dx will vanish, dz by dx will vanish, dt by dx will also vanish. So these three terms will become eventually 0. So what I get is yzt. Okay, as a result what will I get is dx by dx will be 1. So I will get simply yzt. Okay, so instead of writing that y, z and t are constant with respect to x every time, I simply replace this complete d symbol with this symbol. Okay, this symbol. So yes, as soon as I replace with this symbol, it is quite obvious that these terms will be 0. Okay, so ultimately you will get yzt. Okay, so the thing is, instead of writing x, y, z, t equal to y, z, t, when y, z, t are constant with respect to x, I simply write like this. Okay, this is more convenient. Okay, so this if I write this much, then instead of writing this much, I will convey the message like this. I will use partial differentiation symbol, and partial differentiation symbol will mean this, both mean the same. Okay, but if I don't specify this thing, if I don't specify this thing, and if I only write that d by dx of x, y, z, t, if I only write like this, then it means that y, z and t are not constant with respect to x. So as y, z and t are not constant with respect to x, as soon as you take the derivative, okay, these are not constants with respect to x. So as soon as you take the derivative, you will get dx by dx y, z, t. Okay, then you will get x dy by dx. Now dy by dx is not 0 because I have told that y, z, t are not constant with respect to x. So it will become like this. Then I will get ultimately xy dz by dx. Okay, again dz by dx is also not 0 because I have mentioned it that y, z, t are not constant with respect to x. So these terms will not vanish. Okay, so xyz dt by dx. Okay, so again this term will also not vanish. So this term will not vanish, this term will not vanish, this term will not vanish because x, y, z are not constant with respect to x. Okay, so this is the thing. So this is the difference between complete derivative and partial derivative. Hopefully you got the thing. Okay, now we will move on towards time independent Schrodinger equation or steady state form of Schrodinger equation. Okay, let's move on towards that. And I have already uploaded the notes on Telegram. You must have seen them. If you haven't joined the Telegram yet, then please click on the link in the description. The link will get you to the Telegram. Okay, and you can join it and take the benefit of free notes over there. I have put all the notes of paper 1 and paper 2 over there. Okay, so just have a look at them. Okay, so and they are complete notes, 100% notes. The only thing is they haven't been arranged in sequence. Okay, they 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 are not in sequence. They are here and there, like some of the topics have been started with the paper 2 PDF is starting from orbital angular momentum. Okay, So it must have started from quantum mechanics, but it is starting from atomic and molecular spectra. Okay. So don't worry about that. You will still have to look for yourself that which topics come first and which come later. But that PDF is 100% complete. This I can assure you. Okay. So when your entire syllabus is over, you can revise through that PDF by downloading it, and for starting from page number 1225 page number, you can go page by page and understand everything very well. Okay, those are my old coaching notes. Okay, those were the paid notes once upon a time. Up to 2021 I used to take money to provide that notes. Okay, because I used to work with an academy at that time. Okay, in the year 2021. But after that I left that job and I become a degree college professor. So that's why now I am not charging any money for that. Those paid notes have been provided for free. So you can go to the Telegram and can surely download those notes and take the benefit of it. Okay, and there is no need to buy any other material because my notes in itself are sufficient along with classes and PYQs. I have already told the strategy on Telegram, so you can join the Telegram. Over there, everything has been written. Okay. So time independent Schrodinger equation or steady state form of Schrodinger equation. Let's put the heading time independent. Time independent Schrodinger equation, which is also called as steady state form of Schrodinger equation. Okay. This is also called as steady state form of Schrodinger equation. Okay. So what does this actually mean? Okay. So when the potential energy, okay, when the potential energy V does not depend explicitly, does not depend explicitly, does not depend explicitly on time and is a function of R only. Okay, and the total energy E, total energy E is constant. The wave function, the wave function psi R comma T. Okay, we have denoted it by capital psi because it is what, it is a time dependent one. Okay, so for time dependent wave function I have written capital psi over here because it is a function of position vector and the time both. Okay, position vector and time both. Okay, can be written as the product of two separate functions, phi psi of R. Okay, a function of only R and phi of T a function of only t. Okay, that is psi of r comma t is equal to psi of r multiplied by phi of t. Okay, now let us understand this. Now we have the potential energy function. Okay, we have what potential energy function we have. Okay, and suppose the when the potential energy does not depend explicitly. Okay, potential energy function will be there. Okay, so potential energy function can be of two types. Potential energy function can be of two types. It either it may be time dependent, means potential energy might be a function of r comma t, or it might not be a function of r comma t. Okay, it might be a function of r only sometimes. So sometimes the potential energy v is a function of r only, and sometimes the potential energy v is a function of t only. Okay, so in case if the potential energy v does not depend explicitly on time. Okay, if the potential energy v does not depend explicitly on time. Okay, and is a function of r only. Okay, and is a function of r only. Okay, so t term is absent in the expression for potential energy v. When we write the potential energy function v, then t term will be absent in it. Okay, only r term will be present in it. Okay, so when the potential energy v does not depend explicitly on time and is a function of r only. Okay, and the total energy E is constant. Okay, it is a function of R only, and the total energy E is constant. Okay, total energy E is constant. The wave function psi r comma t. Okay, total energy E is constant. So the wave function psi r comma t can be written as the product of two separate functions. Okay, can be written as the product of two separate functions. The wave function psi of r comma t can be written as the product of two separate functions, psi r, which is a function of r only, and phi t, which will be a function of t only, right? So in that case, when is this applicable? When the potential energy v is a function of r only. Okay, so in its expression t term is absent. When we write the expression, t term is absent in it. Okay, and also the total energy E is constant. Okay, total energy is E is also constant. In that case, this is the expression for psi which we get. This is the expression for psi which we get in that case. Okay, means you can clearly write capital psi r comma t equal to small psi r multiplied by phi t. Let me give you an example of this. Okay, let me give you an example of this. Suppose I have a function. Let us consider one dimensional. Let us consider one dimensional. Okay, so suppose if I have like this. Okay, x comma t. Okay, so suppose I have like this, not x comma t. Let us consider r comma t only. Okay, let us consider r comma t only. And if I have, suppose the function is like this, 3x square t square I cap. Okay, plus 6x square t cube. Okay, j cap. Okay, and the function says further that 6y square z cube t to the power 4 k cap. Suppose this is your psi value, means time dependent Schrodinger wave equation. So this is the wave function which is given like this. So clearly I had told you that in case when v is constant, so suppose v is not depending on time, is a function of r only, and total energy E is also constant. Okay, so wave function, this wave function can be written as a product of two separate functions. I had told you, like this and this, okay, and vice versa is also true, okay, vice versa is also true. Now if this is the function given to you, then you can clearly see this thing. Suppose over here it is square only, okay, suppose that it is square only, suppose it is square only, then clearly over here what you can do is this t square can be taken outside common, okay, this t square can be taken outside common. So as soon as you take that outside common, what will happen? Ultimately you will get 3x square I cap, okay, plus 6x square j cap. You will get this ultimately plus, okay, 6x square j cap, you will get this, and you will get 6y square z cube k cap. You will get like this, okay, this is the first term, and the t square will come out common over here. T square will be outside of the bracket, t square is outside. So okay, so this is basically this for t square will be outside of the bracket, so this can be represented as phi t, and this entire function over here can be represented as psi of r, okay. So in this way, as we can write this capital psi r comma t as a product of two separate functions, which is a function alone of r and a function alone of t, then this function is clearly from this expression, as you can take out t square common, so this can be represented as phi t into psi r, okay. So this is the function where we can clearly state this thing, that in this case v will be your function of r only and e will be constant. We can conclude from here, okay, we can conclude from here according to this statement, okay. But if the wave function is like this, suppose, okay, if the wave function is like this, suppose this is basically r vector, okay, this is r vector, and the function says that it is let t 6x square t square I cap, okay, plus 6y square t cube j cap, right, plus 6z square t to the power 4 k cap. If it is like this, then clearly even if you take t square common, even if you take the t square common, then you are left with 6x square I cap plus 6y square t j cap, okay, plus 6z square t cube, okay, not t cube, t square k cap, okay. So clearly you got phi t, but this is not phi r, psi r, this is not psi r, okay, it is psi r comma t again, it is psi r comma t again, it is not psi r, because here the t term is coming. So over here we can conclude that, v r, so it will be a function of r and t both. Your potential v will be a function of r and t both, because you are not able to write this as equal to psi of r comma phi multiplied by phi of t. You are unable to write like this, okay. As you are unable to write like this, it is very clear, that in this case the potential will not be a function of r only. The potential of the particle will be a function of r and t, and also e will not be a constant over here. In this case you can conclude this, because you are not able to write psi of r comma t as a function of psi alone, psi r alone, and phi t alone, okay. When you try to find out phi t, if you try to separate phi t, then even then you get a function which is psi r comma t only, okay, in this case, because when you were putting t square common from here, still the t term remains over here, right. So this is a case where the potential will depend on R and T both, and E of the particle, energy of the particle, will also not be a constant. Okay, so hopefully you got this, the meaning of this statement, right? Now let's move on towards our next topic. Okay, so I clarified that thing very well. Now we will write another statement and understand it also. So what you got is that you got this thing, right? Phi of t. Now use this in time dependent equation. Okay, so what was your time dependent equation? I won't write it again. Okay, when you use this relation, when does this relation hold? With this relation hold, this relation holds when v is a function of r only. Okay, not t, no t term present. Okay, no t present in the potential energy function. Okay, and total energy E is also constant in this case. Okay, so in that case this will hold good. Okay, so this will hold good. So clearly if we put this relation, so this is a case similar to this wave function. This wave function was very similar to this, right? This wave function, in this wave function what happened is that as soon as you put the t square common, when you take out the t square common, you get phi t, and when you keep 3x square I cap, 6x square j cap, 6y square z cube k cap, this will be your psi r. Okay, so this can be represented as a function of r only and t only. Okay, so this case is this one. Okay, which we are talking about. So over here v is a function of r only, not t, and E also, the total energy of the particle E is constant. Okay, now if you use this expression in the Schrodinger time dependent equation. Okay, what was Schrodinger time dependent equation? I had already told you. Okay, so in the time dependent equation, what was the sequence? Let me see. Okay, yes. So this is basically your time dependent, okay, equation. If you use that relation, that psi of r comma t, if you use this relation in this equation, this time dependent equation, if you use this relation, okay, r comma t equal to psi of r multiplied by phi of t, if this relation is holding good and you use it in this green expression, which is time dependent Schrodinger equation, ultimately the thing which you get is like this. The thing which you get is, okay, let me write over here, using this in Schrodinger time dependent equation, using this in Schrodinger time dependent equation, time dependent equation, it is found that if you use that in the time dependent equation of Schrodinger, it is clearly found that this will be your case. Okay, okay, let this be suppose equation number 3. Okay, let this be equation number 3. So when you put it in that time dependent equation na, which I had shown you right now in the previous slide, when you put this relation over there, this relation when you put over there, then you get this relationship. Okay, this is the relationship which you get. Okay, and if you take the uh, potential on one side, okay, take multiply these two and take this product on the right hand side. Okay, so whenever you do that, you will you had this thing right in your hand. Okay, let me show you all the steps, so don't worry. We are okay, psi r equal to e psi r. Okay, so just take it on one side. Okay, so when you write it like this, okay, plus v r psi r equal to what, e psi r. Okay, now take this term to the right hand side. So what will you get? We will simply get, okay, we'll simply get like this. Okay, got it? So this is the thing which you got. Then you will take this to the right hand side again. So when you take that to the right hand side, you will simply get psi square phi r, okay, equal to minus 2m by h cut square, okay, e minus v psi r. Okay, like that you will get. Then what will you do? Put bring this to the left hand side. Then when you bring it to the left hand side, you will simply get like this. Okay, plus 2m over h cut square, okay, e minus v psi r is equal to 0. Okay, let this be equation number 4. Let this be equation number 4. Now the one dimensional equivalent of this equation, you know this very well, that the expression which we got is like this. Okay, psi square del square psi r plus 2m by h cut square, okay, e minus v psi r, okay, is equal to 0. Then as soon as you write its one dimensional equivalent, so when you write the one dimensional equivalent, you will get ultimately del by del x square psi x plus 2m by h cut square e minus v. Now I am writing the one dimensional equivalent, right? So what will happen in one dimension? What happens in one dimension? Let us suppose that only x direction is there, y and z are prohibited. Okay, suppose that only x direction is there, y and z are prohibited. Only this direction is allowed, this direction is prohibited, and this direction is also prohibited. So what will happen to your Laplacian is that your Laplacian, the Laplacian which is given like this, your this Laplacian which is given like this, it will, this term will be gone, this term will be gone, because the motion has been restricted in one dimension. So as motion has been restricted in one dimension, you will get del 2 by del x square simply. Okay, and what happened to this r position vector? This r position vector became x. Okay, and this r position vector became x. Why it became x? because you know this very well, that your position vector r is given by x I cap plus y j cap plus z k cap. Okay, now as you have restricted the y and z directions, so clearly this term will be gone and this term will be gone, because y and z will become 0. So your r vector comes out to be equal to x I cap. Okay, so as r vector equals to x I cap, you can clearly write that r is equal to x. Okay, and you can clearly, because you can quit the vector sign in one dimension. In one dimension, even if you don't write the vector sign, it doesn't matter. So your r vector will eventually turn to x, and your r vector will eventually turn to x. Okay, so this is the expression which you got over here. Okay, so what we got finally, the expression which we got is like this. Okay, the final expression which we got is like this: plus 2m over h cut square e minus v psi x is equal to 0. Now you only tell me. Now observe this term very carefully. Observe this term very carefully. If you observe that term very carefully, so suppose your psi of x is there and it is a function of x only. It is only a function of x, right? Because you have restricted the motion in one dimension. So it is a one dimensional equivalent. So if I take the del square by del x square, okay, of 3x square, okay, if I take it 3x square, if I take it double partial derivative, if I take, what will happen? The thing which will happen is, first of all I will get del by del x 6x, right? 6x I will get, and then after that I will get 6. Okay, if I take the partial derivative, and if I take the complete derivative, okay, if I take the complete derivative, even then I am going to get the same only. Why I am going to get the same? I had told you clearly this thing, that if y, z and t term are not at all present in the expression, see the values of d and del, okay, del by del x and d by dx, their values will be different, will have different values. If the function written over here, okay, okay, so if the function written over here is a function of four things, okay, that is x, y, z and t. If the function is a function of x, y, z and t, all the four variables, then it will have different values for these derivatives, will have different values for del by del x, that is partial differentiation will yield different value, and complete differentiation will yield different value. I had told you in the starting of the class this thing, will have different value for partial derivative and complete derivative. I had clearly told you this thing in the starting of the class. Okay, now clearly, if i if I have only one variable x, okay, but in case if I only have one variable which is x, I don't have y, z and t, then clearly your complete derivative and partial derivative will be the same. Okay, your complete derivative and partial derivative will have same values. So I can write over here del by del x and d by dx. Del by del x and d by dx will have same values, because psi x is a function of x alone. As it is a function of x alone, there are no y, z and t terms. So it is quite obvious that both these terms are going to be evaluated as the same. and as both these terms will be evaluated to be the same, so clearly this concept we can apply over here, that instead of writing this del symbol in this equation, okay, in this equation, if we replace this del by d, then it is okay. Okay, so I am replacing del by d, as it is a function of x alone, we get the final form of the equation. What is the final form of the equation? We get it like this: d2 by dx square psi x plus 2m divided by h cut square e minus v psi x is equal to your 0, right? So this is the one dimensional equivalent of your Schrodinger wave equation, time independent. Okay, so in the general form, the time independent Schrodinger wave equation, in the general form is like this. Okay, in the three dimension, this is three dimensional form of Schrodinger independent time independent equation. So Schrodinger time independent equation will have this form in the three dimensions. Okay, and Schrodinger time independent equation in the one dimensional form, it will be like this. Okay, so just remember this and cram these in your head. Okay, just cram these in your head. So we can clearly see that the three dimensional form of Schrodinger time independent equation and the one dimensional form of Schrodinger time independent equation have been derived. And why are they time independent? Why are they time independent? Because no t term is present in the expression of the wave function. Okay, no no t term is present in the expression of the wave function, so it is clearly time independent, because this is also time independent, 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 and this is also time independent. So as everything is time independent, I had already told you that when potential V is a function of R only, I had already told you in the starting, and the total energy E is also a constant. So these terms are also not containing T. These two terms are also not containing T. And this term clearly does not have t, this term also does not have t, this term also does not have t, this term also does not have t, because if t would have been there, then clearly we won't have written it like this. If t would have been there, then we would have written it like this, right? But t term is not there, so clearly this will be your time dependent independent one. Okay, these two equations will be your time independent. This is one dimensional and this is three dimensional. Okay, this is three dimensional. Got it? Yes. So now we will move on towards eigen functions and eigen values. Okay, these things will come in detail in the upcoming classes. These things are going to come in detail, but for the time being, let's have some brief introduction about eigen functions and eigen values. Okay, eigen upcoming classes, this will come in detail: eigen functions and eigen values. So E equal to your total energy is equal to your sum of kinetic energy Total energy is equal to sum of kinetic energy and potential energy, right? So you can write it like this, that p square by 2m plus v. Okay. So your E minus V will be clearly equal to P square over 2m, right? So now equation number 5, which we have written over here, the one-dimensional form. Okay, the one-dimensional form. What was the one-dimensional form of Schrodinger wave equation? The one-dimensional form of Schrodinger time-independent wave equation. This is the one-dimensional form of Schrodinger time-independent wave equation. This was your one-dimensional Schrodinger time independent equation. Time independent, one dimensional. Now we know this very well, that E minus V has come out to be equal to P square over 2m. Okay, so now as E minus V has come to be equal to P square over 2m, so you can clearly put this value over here. So when you put this value over here, this term you will get like this, that E minus V will be equal to your P square by 2m. So 2m by h cut will come here. E minus V will be P square over 2m. Okay. Psi x is equal to 0. Okay, then 2m and 2m will cancel out, right? 2m and 2m will cancel out. Then finally what will you get is d2 d2 psi x by by dx square plus p square over h cut square. P square or h cut square psi has come out to be equal to this. Okay, so let this be equation number 6. Okay, so now when you will put various values, you know this very well, that this equation will have different values for different p. Okay, for the different momentum, p is what, your momentum of the particle, right? Now if you put the different values of p, that is momentum, and you solve this differential equation, then clearly you will have different solutions, right? Psi 1, psi 2, psi 3, let those be the solutions. Okay, so let this be equation 6. So I will write over here. Okay, I will write over here several solutions of equation 6. Okay, are obtained. Okay, several solutions of equation 6 are obtained for sets of values, for sets of values for sets of values of total energy, for sets of values of total energy E1, E2. Okay, sets of values of total energy E1, E2, etc. up to En. Okay, so for different values or sets of values of En, if your E value will be different, then your P value will be different. Okay, so if your E values are different, suppose E1, E2, E3, E4, E5 up to En, you have different E values. And if suppose you have got different P values, if you get different P values for different E values. Okay, so when you put different values of P over here, like P1, P2, P3, P4, P5 up to Pn, then obviously this there will be n equations will come, and those n equations will have different solutions for psi x. Psi x will have different solutions, because when you solve this differential equation na, you will get different values of psi as the roots of this differential equation. Okay, so that differential equation when you solve, you will get different roots. Okay, and when you get the different roots, then those will be the eigen functions. Okay, so let me write over here. Several roots of equation 6 are obtained for sets of values of total energy E1, E2, and momentum will also be, right? Let me write over here. And momentum and momentum P1 P2 and momentum P1 P2 up to Pn. The wave function psi1 is obtained. Okay, the wave function psi1 is obtained when so psi1 wave function will be obtained when p equal to p1, okay, and e equal to e1, right? The wave function psi2 is obtained. Psi2 will be obtained. This is self-explanatory, okay? When p equal to p2 and e equal to e2, right? The wave function this is obtained when this is the case, okay? So all these n values of psi which you get when you put p1, this will become psi1. The root will become psi1. When you put p2, the root will become psi2. When you put p3, the root will become psi3. Okay. So like that you will keep on putting the values, and you will get many functions. You will get actually n functions. Okay. So and in general the wave function psi n is obtained similarly. Okay. So wave function psi n is obtained when it will be obtained when p equal to will be your pn, okay, and e will be equal to your en, okay. So in that case you will get different values of psi. So those will be psi n. So psi n corresponds to this. Similarly psi n minus 1, that will correspond to p equal to pn minus 1, right, and e equal to en minus 1, right. This is quite obvious. So yeah, these all these values which we have, psi 1, psi 2, okay, psi 3, right, psi 4 up to psi n, all these are basically your eigen functions, okay. All these are basically your eigen functions, and when you put the values p1 p2 p3 up to pn, okay, you will get basically eigen values of momentum, eigenvalues of momentum. And when you have these things, okay, all these n values of e, right, all these are basically what eigenvalues of energy. These are basically eigenvalues of, okay. So in this way you are this is the thing, okay. Now we will move on towards our next concept, okay. We will now move on towards our next concept. So up to now, what the summary of what we have seen till now, the summary can be written over here. So let us write the summary of what we have seen till now. So let us have one summary. So the summary says that summary says that number one, time dependent equation, time dependent Schrodinger equation will be like this. This is the summary of what we have learnt till now, okay. Is equal to your I h cut del by del t, right, psi r comma t right? And this is basically three-dimensional form. Okay, this is three-dimensional form, right? Time-dependent Schrodinger equation. This is the three-dimensional form. Now, one-dimensional form of the same. One-dimensional form of the same will be like this. This is the summary of what we have learned till now. Okay, we are writing the time-dependent ones. We are writing the time-dependent ones. Is equal to your I h cut del y del t psi x comma t. What is this? This is basically one dimensional. What is what one dimensional? One dimensional Schrodinger time dependent equation. Okay, now the second thing is time independent equation, right? Time independent equation of Schrodinger. Now we will write over here that psi square, not psi square, del square means Laplacian plus 2m by h cut square e minus v psi r, right, is equal to 0. This is what your three-dimensional form. Okay, and what is the one-dimensional form? One-dimensional form clearly can be written like this. Okay, this is the one-dimensional equivalent of Schrodinger in time-independent equation. Schrodinger time-independent equation in one-dimensional form. Okay, this is one-dimensional. Okay, now we will move on towards this thing that we had seen this very well. We had seen this very well that your psi of r comma t could be written like this. This can be written like this. We had learned till now, right? Yeah, in which case we can write like this in the time independent. Okay, in time independent form of Schrodinger equation. Okay, in time independent form of Schrodinger equation, we can write like this. Okay, now clearly you can see that the term this term is called as the amplitude of the wave function. Okay, so let us write over here psi r, okay, gives the amplitude of the wave function psi r comma t. Okay, so time independent, so time independent form of Schrodinger equation. So time independent form of Schrodinger equation is known as amplitude equation. Is known as amplitude equation, right? So I had clearly told you this thing that psi of r comma t can be written in time independent form like this. So let me tell you with a practical example. Okay, suppose you have two kind of time dependent wave functions. Okay, suppose this is the time dependent wave function number one. Okay, your wave function number one looks like this. Okay, your wave function number one looks like this. Your time depend first function looks like this, right? Your time dependent function. So clearly, if we take the t square common out of here, if we take t square common, what will happen? T square is common, so it will become like this. Okay, plus 6z square k cap. Okay, so this term is known as amplitude. Your this term is known as amplitude, and it can be represented like psi of let me show the notation over here. This is basically your capital psi. Okay, this will be your capital psi. Okay, so yeah, this will be your small psi. Okay, and this is what, this is your phi t, because this is a function of t alone. Okay, so this is basically phi t, and both are in multiplication, like the thing which has been written over here. Okay, now in case if this would have been different, this sometimes it is possible that this might not be representable in this form. Okay, so when this is representable, okay, let me show you. When this thing is representable in this form, when it is representable in this form na, then only time independent equation can be written. Then only time independent equation can be written. Okay, it can be written then only when this, let me write over here, when psi of r comma t equal to psi r multiplied by phi t. Okay, this is what, this is your when this can be written. Okay, when this can be written, only then time independent form of Schrodinger okay, when this can be written now, only then time independent form of Schrodinger wave equation can be written, when this can be written. And but if this cannot be written, in case, okay, for example, if I have a wave function like this, so this was possible in which case? When the wave function was like this. Okay, have a look at this now, have a look at this. When the wave, or sorry, when the wave function was like this, 3x square t square, okay, like this was your wave function. So in this case, you can clearly take t square common from this. You can clearly take t square common from this. So it is representable in this form. Okay, so in that case, this will be the case, and in this case, time independent form Schrodinger wave equation can be written. Okay, but in this case, the time independent form of Schrodinger wave equation cannot be written. In which case, if the wave function is suppose like this, your wave function says that 3x square t square I cap, okay, plus 3y square t to the power 3 j cap, okay, and 3z square t to the power 4 k cap. Suppose this is your equation, then clearly, even if you take t square common from here, even if you take t square common from here, still the t term will remain here. Okay, the t term will remain over here. Here t to the power 1 will remain, and in the last term t to the power 2 will remain. Okay, so clearly this is not equal to psi of r comma phi of t. Okay, because although phi of t has been obtained, okay, although phi of t has been obtained, okay, although phi of t has been obtained, but this term is not purely a function of r. This term is not purely a function of r. It still has t term in it. It still has t term in it. Okay, so this is the case. So in this case, so let me write over here that if psi of r comma t cannot be written in terms of r and phi of t, then time independent time independent form of Schrodinger wave equation cannot be written in this case. Okay, so time independent form of Schrodinger wave equation cannot be written in this case. And what is this called as? What is this called as? This is basically called as the amplitude. Okay, so let us write over here. Okay, psi r gives the amplitude of the wave function. Okay, it is basically amplitude of wave function. Okay, it's basically amplitude of wave function psi. Okay, this is capital psi because it is time dependent. So this is amplitude of the wave function this. So that's why time independent. Okay, that is why time independent form of Schrodinger equation, time independent form of Schrodinger wave equation, right, is also known as amplitude equation. Is also known as amplitude equation. Time independent form of Schrodinger wave equation is also known as your amplitude equation. That's why. Okay. Now we will do a problem from the year 2009. We will do year 2009 PYQ. Okay. PYQ of the year 2009 we are going to do now. Okay. So let us write the question to show. Okay. Show that the phase show that the phase of the time dependent part of the wave function is given as, okay, psi t equal to psi of 0 e to the power minus I e t over h cut. Okay, so this was asked in the year 2009 and this question is same as, or okay, this question is same as this, to show that time dependent part, okay, time dependent part of all solutions of Schrodinger wave equation in 1D has the structure, okay, has the structure phi t equal to e to the power minus I e t over h cut, okay, phi t, okay. Now this is also phi, okay, this is not psi, this is phi, okay, because when it is a function of t we do not represent it by psi, we represent it by phi, okay. So this is also phi, this is also phi, okay. So we can think that this is the question of 2009, and if the question is asked in this form, okay, if the question is asked in this form, then also it is the same. This question is also the same, and this question is also the same. Both are going to be the same questions, okay. So let us now look at the solution of this question which had been asked in the year 2009, okay. But before that, let me take some water, okay, let me take some water before that. Yes, so hopefully everything is good now, okay. So we had seen that a question was asked in the year 2009, okay. The question says that show that the phase velocity of the time dependent part of the wave function, okay. Show that the phase of the time dependent part of the wave function is given as this, okay. Or is to show that the time dependent part of all solution of Schrodinger wave equation in one dimension has the structure this, okay. So some students ask the doubt over here, some students ask the doubt that here this is pronounced as phi, okay. This is basically your phi. What is this pronounced as? This is pronounced as phi, okay. So now as this is phi, so phi t equal to e to the power minus I e t divided by h cut is the thing, okay. Now as this is the thing, so eventually you will have to basically what, you will have to see at this and tell me whether this form, whether this form or whether this form, both are same or not. So students ask me that how can these two questions be the same, because here it's asked like this and here it's different expression, okay. So you can clearly see this thing that in the both the questions are same, I am saying, then how come they have different expressions. On the in the first question it is given in the first language, it is given that prove that the time dependent part is like this, okay. Prove that it is like this, it is given in the first part, and in the second part it is given that psi t equal to e to the power minus I e t divided by h cut, okay. So I am saying that either to prove this or either to prove this, there is same requirement, there is no difference between the two. Why there is no difference between the two? Because this is simply a constant. The quantity you are seeing over here, this quantity, that is simply a constant, okay. So let me write over here that psi, not phi of 0 is clearly a constant. As that is a constant, so this function and this function are going to be the same, because you have learnt in your lower classes, you have learnt in your lower classes that y equal to x, okay. Suppose this is the straight line, This is the straight line equation. Then clearly this straight line equation will be like this. Okay, but you have learned that y equal to mx plus c shows a straight line. So y equal to x is just a special case of that. Okay, so if I write this as y equal to x, so even if I multiply suppose this x by m, still it will show a straight line only. Only thing is its slope will change. Okay, this has a slope equal to 1, but here the slope will be equal to m. Okay, here the slope will be equal to m. Okay, so slope means tan theta. Okay, slope means the theta angle we are taking its tan. So when we take the tan of that, we get the slope basically. So you have clearly learnt in your lower classes that y equal to x and y equal to mx plus c both represent straight line only. Okay, so this implies that what does this imply? This implies that multiplying by a constant value does not change the nature, okay, or graph of the nature or graph of a function. That's why multiplying by a constant value does not change the nature or graph of a function. That's why your phi t, okay, if you write it like this, e to the power minus I e t over h cut, and okay, and phi t equal to e to the power minus I e t over h cut. Okay, okay, this expression and this expression are basically equivalent. Okay, so it has been written multiplying by constant value does not change the nature or graph of a function. That's why this and this, okay, represent the same function. Okay, so this is basically an arbitrary constant. Okay, it is basically arbitrary constant. Okay, so its value we can choose. Okay, we are free to choose. So as we are free to choose its value, why not choose it to be equal to 1? Why not choose it to be equal to 1? As soon as we choose it to be equal to 1, we get this thing. Okay, and I told you this clearly that y equal to 2x, y equal to 3x, y equal to x, y equal to 4x, y equal to 6x, y equal to 7x. All these are identical. Identical with respect to what? Identical with respect to nature of the graph. Nature of the graphs remains same. Nature of the graph is same. Okay. Similarly, if I say that x square plus y square equal to 16, and if I say that x square plus y square equal to 14, and if I say that x square plus 4y square equal to 12, all these basically all of them represent circle only. All of them are representing circle, because this is going to be a circle This is going to be a circle with origin at 0 comma 0, and radius will be 4 centimeter, right? In this case, okay. And in this case, again the origin will be 0 comma 0, again the origin will be 0 comma 0, but radius will be root 14. And in this case the origin is going to be at in the third case the origin is going to be at 0 comma 2. Okay, 0 comma what we can say, it is going to be yes, no, it is also going to be so whatever it may be, but this also represents circle only. That's what I meant. Okay, I just mean that whatever may be the origin, whatever may be the radius, but even if we change the constants, even if we change the constants, even if we change the constants by which we are multiplying, and what the constant which we are adding, even if we change them, still the nature of the graph is going to be the same. Okay, so as the nature of the graph is going to be the same, clearly you can say this thing, that it is going to be that only. Okay, so that's why we are taking this phi of 0 over here as to be equal to 1. We are taking it deliberately in order to ease our job. Okay, in order to ease our job. So now let us solve that 2009 year question. We had to show that phi t equal to phi 0 e to the power minus I e t over h cut, right? We had to show this. Now how to show this? You know this very well. Now let us look at the proof. Let us look at the proof. So clearly you have this thing that we are talking about. What are we talking about? We are clearly talking about time independent. Okay, we are clearly talking about time independent Schrodinger wave equation. So we are clearly talking about time independent one, right? So as the time independent Schrodinger wave equation is being talked about, so clearly we can write this equation. Okay, this equation we can write because this is the case given in the statement below. So we can clearly write this thing. Okay, now instead of writing this, okay, instead of writing this again and again, that this is x comma t and this is basically your psi of x multiplied by phi of t. Okay, instead of writing the arguments, okay, instead of writing the arguments x and t again and again, I will replace it by phi psi multiplied by phi. Okay, I am writing it because we will write, we will not write these arguments again and again. To ease our job, we will not write these arguments again and again to ease our job, and so we can write it to be equal to psi multiplied by phi, psi multiplied by phi. Okay, now take the partial differential on both the sides. Okay, you know this very well that we have got this thing psi multiplied by phi. Now we will take the partial differential on both the sides. Okay, partial differentiation with respect to time on both the sides. You know this very well that this is a function of x, right? This is a function of x. So when we take the partial differentiation with respect to time, so clearly x will be treated as a constant. x will be treated as a constant in, well, let me write over here, x will be treated as a constant, x will be treated as a constant while taking del by del t. So that's why this quantity is going to come out of the partial differentiation with respect to t. Okay, and this will remain. Let this be equation number 1. Okay, I had told you in the beginning of the lecture that why we can take out this psi out of this, because when we are taking partial differentiation with respect to t, all the terms other than t will be taken as a constant. I had told you na, the difference between partial differential and full differential operator. In the partial differential operator, we are differentiating with respect to t, so all the variables other than t will be taken as a constant. But in full differentiation, what happens? If we take full differentiation, let me write over here. Okay, if we take full differentiation na, if we take the full differentiation, okay, if we take full differentiation, which is denoted by d, okay, then you will have to apply the uv formula. uv formula you will have to apply then uv formula, because this is full differentiation, not partial. Okay, then the according to that formula, what will come? Psi d psi by dt phi plus psi d phi by dt. Okay, let me write over here. If we take the full differential, if we take full differential of psi with respect to t, then we are going to eventually get this thing. Okay, but we don't want this thing, that's why we are using partial differential operator. We are basically going to get this in the case of full differential. Okay, uv formula has been used. uv formula has been used, but we are taking here partial differentiation, so that's why the function of x will be treated as a constant in front of a differential with respect to t. So in front of a differential with respect to t, function of x will be taken as a constant, so it is going to come out. Okay, so ultimately you got this, so let this be equation number 1. Okay, now we know this very well. That was equation 1. Now what we have got? We have this thing, okay, equal to x t, okay, equal to a e to the power I by h cut, okay, xp minus et. From where did we get this? We know this very well, right? We know this from the elementary fact. We know this very well from the elementary fact that psi of x comma t has this equation of a plane wave. You might have heard. You might have heard about equation of a plane wave, right? So from there we got this concept. Okay, so this formula is quite understood. You have to keep this formula in mind. It is a well obvious formula. Okay, so now uh, from the equation of a plane wave, we will basically write, we will take the differentiation with respect to t on both the sides. Okay, so we will get a e to the power I by h cut, right, xp minus et. Okay, xp minus et, right. Now how did we get this term? Let me explain you. Okay, let me do the differentiation in the other slide. Okay, so we have this clearly that psi, capital psi is equal to your a e to the power I by h cut, right? I by h cut xp minus et. Now you have to take the partial differentiation with respect to time. So what will you get? Partial differentiation with respect to time. Let me write partial differentiation with respect to time. So clearly a is going to come out as it is a constant. Okay. So a will come out, and eventually you are left with this thing xp minus et. Okay. Now when you differentiate, so clearly you can see this thing that this will be equal to e to the power I by h cut. Okay, xp minus et, this remains as it is, and we get del by del t of I by h cut xp minus et, right? Now when you take the partial differentiation, you will basically get all these things as equal to 0, and eventually you will get minus I by h cut. Okay, so what is the differentiation of this? You know this, na? You will expand this, you expand this, multiply this by this, and multiply this by this. So differentiation of this term multiplied by this term, the differentiation with respect to time is going to be 0. But this term, as it contains t, so clearly minus I e by h cut will come out. Okay, minus e I by h cut, this term will come out, and differentiation of this t will be equal to 1. So eventually in the final step what you get is this. Okay, minus I by h cut, right? E a, okay, e to the power I by h cut, right? xp minus et, right? xp minus et, right? Now this term, what is this term? This term, what is it? This term, what is it equal to? Let us write over here. Okay, this term, this term is equal to psi again, right? So you will get minus I by h cut e psi, right? And your psi is equal to then psi phi, as you know this very well, that in the beginning we had told this thing that psi x comma t, capital psi x comma t equal to psi small psi phi, right? So we will eventually replace this in the form of this. Okay, e psi phi. Okay, so let this be equation number 2. Okay, so what is the equation number 1? We know this is the equation number 1, and we know that this is the equation number 2. Okay, now see this very well, that uh, what we can do to this, we can do something over here also. We can do something over here also. Okay, so let me write in the next slide only. Ultimately what we got is that this thing by del t is equal to your minus I by h cut, okay, e psi phi. Okay, now write this psi equal to psi phi. Okay, so the left hand side becomes like this. Okay, and the right hand side becomes like this, right? Now you know this very well that we are taking, this is basically your small psi is basically a function of x only. and your phi is a function of t only, right? So as these are the facts, so you can take this out, you can take this out of the differential sign. So as you take that out of the differential sign, so eventually you get psi del phi by del t, right? And ultimately this will be equal to, this term will be equal to this term, right? So those two terms are equal. Okay, so what you get is psi del phi by del t, okay, equal to minus I by h cut, okay, e psi phi. Now these two terms are going to cancel out from the LHS and RHS. These two terms are going to cancel out. So ultimately you get by del t, okay, sorry, really very sorry, okay, del t is equal to your minus I by h cut e phi, okay. Then eventually when you take, now you know this very well that this thing this thing can be brought in the left hand side, this thing by the method of variable separation, okay, by variable separation, variable separation, okay. So we will separate the variables eventually, so we will get del phi by phi, okay, equal to minus I by h cut e dt, okay, e dt. So why has the partial differentiation, why has the partial differentiation turned to full differentiation, okay? So let me see, yes, why has the partial differentiation turned into full differentiation symbol, why has the del turned to d over here? Because you have basically uh, taken these differential you are doing, never write that we are multiplying by this on both the side, okay, never do this mistake in the exam, okay, never write that we are multiplying both side by del t, it is wrong to say like that, okay. We are not multiplying with del t on both the sides, it's just that for the sake of our convenience in the mind, we assume that we are multiplying both side by del t, we are assuming like that for our sake of convenience, for our imagination purpose, we are assuming it like that, and this will cancel like that, we are assuming in our mind for our convenience. But it is wrong to say, it is wrong to say that we multiply both side by del t, it is wrong to say like that, okay, because these are not ordinary different not ordinary mathematical quantities, these are not ordinary numbers, these are basically differentials. So for the differentials you can never say, okay. So if a differential comes like this, okay, suppose there is a differential like this, okay, suppose there is a differential like this, dx by dt, dx by dt equal to suppose 5, okay. So we write like this then 5 dt, but it is wrong to say, it is wrong to say right over here, it is wrong to say multiplying both sides by dt, as dt is not an ordinary number, but it is a differential quantity. Okay, it is a differential quantity. So so ordinary algebra cannot be applied to it. Okay, for the sake of our convenience. Okay, for the sake of our convenience, in the mind we are imagining. Okay, in the mind we imagine. What do we imagine in our mind? In the mind we imagine that we are multiplying both side by dt. We imagine like this. In our mind we imagine like this, that dt is equal to 5 into dt. Okay, then this dt and dt is cancelling out, and finally we get this. In the mind, for the sake of our convenience, for the sake of our convenience, for the sake of our imagination, we are imagining it like this, that dx by dt multiplied by dt will come, and dt will cancel. We are imagining like that, but that is not the case. It is wrong to say that dt and dt are cancelling out. It is wrong to say. Only thing is we are separating the variables. So the correct statement is variable separation. Okay, so correct way to say it is not multiplying multiplying both sides by dt, but it is correct way to say it is the correct way to say is separating the variables, separating the, this is the correct way to say it. Okay, so this was the explanation. Okay, so you have basically done the same thing. Now how this partial differentiation symbol has turned to full differentiation? Okay, how has this come? Because basically you have separated the variables. So as we have separated the variables, we can write we can write d in place of del. Okay, so we can write d in place of del, because the t is in over here now. T is over here now. So clearly it is now the meaning of partial will not hold. Partial differentiation, the meaning will, del meaning will not hold. So we are basically replacing it with d. Okay, so you got this thing, and from this step let us write the next step. Okay, so in the next step we are basically integrating. Okay, d phi by phi, okay, equal to minus I e divided by h cut integration dt, right? So it will become basically your ln ln phi of t, right? Ln phi of t equal to minus I e by h cut into t plus c. Okay, this is quite obvious. Okay, you know this very well, that integration of 1 upon x dx is equal to what? 1 upon x dx integration is ln x. Okay, so from that formula of integration we get this thing, and assume this to be equation number 3. Okay, Now we will apply the boundary conditions. Okay, now apply the boundary conditions. Now apply boundary conditions. Why do we need boundary conditions? Because it is an indefinite integration. Okay, it is indefinite integration, so we have got the constant of integration. Okay, so I am writing over here. Now apply boundary conditions because it was indefinite, because it was indefinite integration, and so we had got we have got, okay, and so we have got constant of integration C. Okay, so boundary conditions we will apply. So we have to find C. Okay, so we that's why we will apply uh, constant of in order to determine the constant of integration. Okay, in order to determine the constant of integration C, we will apply the boundary conditions. Okay, so the expression which we got is like this, right, which can be seen. So let me write the expression again. So we have got ln phi of t is equal to minus I e by h cut t plus c. Okay, when t equal to 0, now when t equal to 0, what will happen at t equal to 0? C is the integration constant. Okay, so when t equal to 0, what will happen at t equal to 0? At t equal to 0, then ln phi of 0, ln phi of 0 will be equal to C. Okay, so the term on the RHS will vanish. Okay, when we take t equal to 0, this term is going to vanish when we take t equal to 0, and as that term is going to vanish, so clearly we will get the constant of integration C value. Okay, so we got this thing. Now we can clearly write this, put this value over here. Okay, so what will you get? Putting that value over there, so ln phi of t will come out to be your I e minus I e over h cut t plus ln phi of 0, right? Now bring this to the left hand side, so obviously you will get okay, minus ln, so let it be, okay, minus I e over h cut t. Okay, then log a minus log b formula. Log a minus log b is equal to log a by b, right? And ln is your log base e, log to the base e is your ln, so logarithmic formula can be applied to it, right? So I am applying the logarithmic formula. So applied that formula, and after applying that formula I got this very clearly. Okay, now you know this very well. What have we got? We have clearly got this, that ln psi t divided by, not psi, phi basically. Okay, it is phi basically. So you have got this thing. Okay, now you know this very well, that log, this can be written as log to the base e. This can be written as log to the base e, because ln is basically log to the base e only, right? So minus I e over h cut t. You can write it like this. Now you know this formula very well, that log b to the base c is equal to a. That implies that c to the power a is equal to b. You might have learned this formula in your JEE time. You must have learned this formula in your JEE time, that c to the power a will come out to be equal to b. Okay, so clearly this raised to the power this will come out to be equal to this. Okay, so from that formula we clearly get that phi t by phi 0 is equal to your e to the power minus of I e over h cut t, right? Then phi t will again will your, okay, e to the power minus I e over h cut t, right? So this is the formula which you got at the final stage. Okay, this is the formula which you got at the final stage. And so time dependent part of the solution. So clearly from here we can see, now this is a arbitrary constant. We already know this, that this was constant of integration, right? This was basically what, constant of integration. So this is arbitrary constant, right? If they see na, over here we had got this in the form of c. We had got this in the form of c, right? So clearly psi of 0 is your equal to e to the power c, right? So it is a constant. E to the power constant is again a constant. So your phi of 0 is clearly a constant. So time dependent part of solution of Schrodinger equation is of the form. So I will write the statement finally. Our proof is done. Okay. So time dependent. So time dependent part of the solution of Schrodinger equation is of the form, okay, e to the power minus I e over h cut t, right? So finally now we know this very well, that this was our case. So we will simply now substitute, and nothing else needed. We will just substitute, right? So substitute the values over here. So as you substitute the value of phi t, okay, so psi x will remain as it is, and in the place of phi t you got this expression which is written over here, minus I e by h cut t, right? And psi of x has remained as it is. So this is the final result which you got. Okay, this is the final result which you got. Thus now we will write the final statement. Thus psi x, okay, thus psi x gives the amplitude, okay, gives the amplitude of the wave function psi x comma t, and phase is given by e to the power minus I e t over h cut, and the phase is given like this. Okay, so this is the proof which we got, hence proved your 2009 question. Okay, now we will move on towards our next question, which is of 2012. Okay, 2012 question, we will move on towards that. So problems on finding potential Vx when psi x and all those things are given. We will basically learn this. Okay.